Okay, welcome back, everybody. Welcome back. Last time we ended with some new notation and terminology involving cycles. So we'll do a little bit more um, practice with those sorts of things soon. So in some of the examples that I do here in a second, I'll work out some of the cycle computation just so you can see a little bit more practice with this stuff. A lot of things you can look up both in the textbook and online. Tons of resources for getting a hold of this cycle notation for permutations. Um, but first, before I do that, I was going to define one more thing before giving some specific groups to mention. So a uh, subset H of a group G with some group operation that you might wonder why we tend to write group operations as multiplications or transposition. It's just because we can eliminate a symbol, right? So when you implicitly write the operation with transposing the elements, so you write a product as AB, the understanding that the product here is the group product, it just lets you get rid of a symbol, right? But this is what we mean by this in the context of a group is whatever that group operation is. Okay, so just like I mentioned, now we're at a point where when we say we have a group G, we're not going to write out what the symbol for the operation is typically. So you're assuming that there is some group operation that has all the properties it needs to. A subset H of a group G is called a subgroup of G if it is itself a group with respect to that same binary operation. If H is a group itself with respect to the same binary operation. Okay. So this group, the symmetry group in objects, has many subgroups. We'll look at a few special ones now. What should I say here? Textbook doesn't mention this, but maybe I'll go ahead and say this just because. It turns out Cayley's theorem says that, and I'm not going to define this notion for groups, but I think you should know it anyway. Every group G is isomorphic. We haven't talked about what it means for a group to be isomorphic to another group, but you understand the concept of isomorphism from linear algebra and from graph theory earlier, that when we call objects isomorphic, it means that in some sense they're relabelings of each other, right? So they are the same object even if we've labeled, say, the vertices of a triangle 1, 2, 3 instead of A, B, C, right? There's an analogy with congruent triangles, right? Congruent triangles are not the same triangle in the sense that you can draw one on the left side of the page and one on the right side of the page. They can't be the same because one's over here and one's over here, right? But they are the same structurally if you're just talking about its structure as a triangle. So in the sense of vector spaces, isomorphic vector spaces have the same vector space structure. Any vector space computation you do in one can be pushed back and forth between that one and the other one. Same thing with graphs, right? If two graphs are isomorphic, they're essentially relabelings of each other. So any sort of computation, any sort of property that one has, the other one must have any sort of property the other one doesn't have, the other one must not have, so on. Okay, so that notion exists for groups. Maybe I'll define it if we have time, like near the end. If I'm on like Thursday or Friday where I'm truly doing like extra stuff, I have some extra time, I might mention it. But anyway, every group G is isomorphic to a subgroup of the symmetric group. Okay, for some n. I could say a little bit more there, but I'm not going to. I'm just saying, so it's kind of a joke when I say that this symmetry group has many subgroups. If we're including groups isomorphic to a subgroup, then it literally contains, in some sense, all groups. This is not, this, you might call this the least important theorem ever, because this theorem is basically useless. It's basically useless in the sense that knowing this does not help you at all. There's basically not a single group theory computation you could ever do where this is helpful. So you might say, whoa, what is even the point of it? Other than just the fact that it's true, right? And I'm just stating a true fact. It's conceptually nice because basically it's, if you like, right, and maybe you've even heard of this when people are kind of talking loosely, they might say that, when you're talking about notions of symmetry, groups always play a role. That's where they're like first introduced in a lot of places. This is like really, really enshrining that. It's saying, well, of course groups play a role because, the symmetry group is kind of like the group that contains all the other groups, in some sense. So yeah, of course it has this this property. We could, like I said, I could say more about this and make this a little bit more precise, but I'm not going to. This isn't going to be very important for us, but I just wanted you to know that, kind of conceptually. I should say it's not a, we'll talk about groups that might have infinite elements. Everything we're talking about right now is finite, so keep that in mind. But anyway, back to this. So here are a few special subgroups. So the first type is the cyclic group. So let pi be a permutation in our symmetric group. Let m be a non-negative integer. What we mean by pi to the m here is pi composed with itself m times. So, for instance, pi to the 0 is the identity for the same reason that this is the identity with normal multiplication. And of course, the identity element in S sub n is the permutation that just fixes everything. Pi cubed, well, this is an example of this. So this is pi composed with itself so that there are m copies. So pi cubed is pi composed of pi composed of pi. Okay. Define by the symbol these corner brackets. This is going to be the set of all powers of pi in this sense, where m is allowed to run over non-negative integers. Necessarily, the members of this set are permutations. This definitely contains the identity. This itself is definitely a subset of the symmetric group. Exercise that you'll do, well, I just gave you your last homework assignment. It's due on Wednesday. It's not going to be on homework. Maybe it'll show up on final exam. Who knows? So an exercise in this section actually shows that it's a subgroup of S sub n. This is called the cyclic subgroup of S sub n generated by pi. Okay. Okay. So, in that way, let's define the following. So, the cyclic group C sub n is the subgroup of the symmetric group S sub n generated by the permutation that is simply the cycle of length n. So, using this previous notation of having a cyclic subgroup generated by an element or by permutation, C sub n is the cyclic subgroup generated by this single permutation that is represented by that cycle. Okay, using cycle notation. Okay. Now, how many elements does this have? N. It has n elements. You might not immediately be able to see that that's what's going to go on here, but if you think about what happens here, this cyclic subgroup, right, is generated by iterating pi composed with itself. So what happens when you compose this thing with itself? Let's see what happens for a smaller n, and then you'll see what it is that's going on here. Let's do this for like C sub 4, right? So quick example, C sub 4. So this is the cyclic subgroup generated by this permutation, 1, 2, 3, 4. So let's see, what is this thing composed with itself? Of course, you know, you will reach a point where you can do this maybe in your head, but let's just write out the powers here to make it a little easier. This is 1, 2, 3, 4. And to make our lives easier, I'm not going to include the composition symbol here. We know that if we have things written like this, this is multiplication in the group, meaning this is a product in the group, which is a composition. So that's one of the key things when you're doing this early group theory stuff is you'll see, because most of these examples are dealing with permutations, they're dealing with elements of the symmetric group. It is, you'll pass back and forth between product and composition, but a product is a composition of these permutations, right? So that's what's going on here. So let's see what this is. Remember, we go right to left here. So 1 goes to 2, and then 2 goes to 3. So in cycle notation, this is 1 and then 3. Here, 3 goes to 4, 4 goes to 1. So I close this cycle. And then next, what happens to 2? So 2 goes to 3, and then 3 goes to 4. So 2 goes to 4. 4 goes to 1, 1 goes to 2. So I close this cycle. So 1, 2, 3, 4 squared, 1, 2, 3, 4 applied to itself, which is exactly this. Think about what this is doing, right? Well, you saw what happened there, right? So 1 goes to 2, 2 goes to 3. So that's the same as 1 going to 3. And, you know, here we see that 3 goes to 4, 4 goes to 1, so 3 is going to 1. That is the result of composing this thing with itself, of hitting this thing with itself. What if I cube this? So 1, 2, 3, 4 cubed. Well, this is 1, 2, 3, 4 squared times 1, 2, 3, 4. And I've already computed this. So this is 1, 3, 2, 4 composed with 1, 2, 3, 4, which is, so 1 goes to 2. Here, we'll start with 1. 1 goes to 2, 2 goes to 4. So this is 1 goes to 4. Here, 4 goes to 1. 1 goes to 3. This is 1, 4, 3. Then here, 3 goes to 4. 4 goes to 2. This is 1, 4, 3, 2. We know this has to close, but let's just check. 2 to 3, 3 to 1. So 2 goes to 1. Okay, and there we go. We got 1, 4, 3, 2. And then what if we raise this to the fourth? You can either think of this as 1, 2, 3, 4 squared squared. So you could do this and have it apply it to itself. Or you could just keep peeling off one copy. So, right, so this is 1, 2, 3, 4 cubed times 1, 2, 3, 4, which is 1, 2, 3, 4 cubed is 1, 4, 3, 2 times 1, 2, 3, 4, which is, if I start with 1 here, 1 goes to 2, 2 goes to 1. So 1 is fixed. Okay, what about 2? Here, 2 goes to 3, 3 goes to 2, so 2 is fixed. Okay, what about 3? 3 goes to 4, 4 goes to 3, so 3 is fixed, which means that 4 is automatically fixed, but again, we're just checking here. 4 goes to 1, 1 goes to 4, so 4 is also fixed. This is the identity. So what is this cyclic group? It consists of the identity, 1, 2, 3, 4, 1, 2, 3, 4 squared, which is 1, 3, 2, 4 in cycle notation, and 1, 2, 3, 4 cubed, which is 1, 4, 3, 2, and that is it. Because, as you see, it cycles back. So just to do this, what if I consider the fifth power? Because technically, right, if we go back here, this cyclic subgroup is all the powers, right? Where m is a non-negative integer, so it's just all the powers. But of course, if I keep going here, once I hit the identity, if I keep going, hitting the identity with 1, 2, 3, 4 is just 1, 2, 3, 4. Okay. So it starts over, it cycles through. And so I only have these 4 elements. This definitely matches this count here. Okay. How to think about this? So C sub n can be thought of as the group of rotational symmetries of a regular n-gon. Okay. So an n-gon, of course, is an n-sided polygon, right? So to see this, I'm just going to draw the picture here. So here's a regular four-gon, which is just a square. And I can label these vertices of the square clockwise in this way, 1, 2, 3, 4 here. So what is C sub 4 in this case? Well, this element corresponds to doing nothing to this picture. In terms of rotations, this would be rotation by 0 degrees. So this is the 0 degree rotation. 1, 2, 3, 4 takes 1 to 2, 2 to 3, 3 to 4, 4 to 1. Right? That's literally what this cycle does. 1 goes to 2, 2 goes to 3, 3 goes to 4, 4 goes to 1 simultaneously. What is that? That is a 90-degree rotation clockwise. What about this one? 1 goes to 3, 2 goes to 4. So 1 goes to 3, 2 goes to 4. That is a 180-degree rotation. Here, 1 goes to 4, 2 goes to 1, 3 goes to 2, and 4 goes to 3. Right? You could say, wow, you did that in a really strange way, right? Instead of going in the other direction. But if we're thinking of this as counterclockwise or clockwise rotation, sorry, then that's the pattern I followed. Of course, you can see this is the same as rotating. Counterclockwise, 90 degrees, but this is it. This is all the rotational symmetries, right? There's no more other than these. And so, thinking of these as a group of rotational symmetries of a regular n-gon, these cyclic groups are important for this class of questions that we had kind of started discussing. Let's go back for a second. What got us off to talking about symmetry groups and all of this in the first place? It was a couple of questions. So the first one was, how many ways can King Arthur and his knights sit at the round table? And since there's no way to distinguish position at this round table, it meant that we needed to treat any sort of rotational symmetry. Of course, a circle has a lot of rotational symmetry, right? We had to treat any sort of rotational symmetry here carefully, because two configurations that could be rotated into each other would be called the same configuration. So in the counting, we don't want to double count things, right? So this sort of question, how many ways can King Arthur and his knights sit at the round table, implies that there's this underlying symmetry, and understanding how to organize that symmetry and deal with it is really the crux of the problem. That's really the main thing that we're doing here. And of course, this group of rotational symmetries of a regular n-gon is going to factor in here, right? Because, of course, how many knights were sitting around the table is going to be the number of vertices in this regular n-gon, if you like, right? That is perfectly fine way to approximate this round table by saying, yeah, the people sitting here are just vertices of a regular n-gon. And because it's regular, there's no way to distinguish a vertex. So we would call things that having the same configuration if one of these configurations could be rotated into the other. That is, if there's a rotational symmetry that that allows you to take one of these configurations into the other. We call it the same configuration. So it's clear why understanding this would be important. This, in fact, this is exactly what we need to understand to answer a question like that. Now, what about this second question? How many different necklaces with N beads can be formed using M different types of beads? In this question, I gave an example down here of like a coloring involving 4 of these things. In this question, something is a little different. Because while it is true that we do need to understand the rotational symmetries of this object, because we're allowed to rotate the objects. The beads are indistinguishable if they're in the same bead type. So all green beads, all red beads are exactly the same. I think here, what did I do? Blue, green, and red. Yeah, so any bead of the same type is indistinguishable from any other bead of that type. So there's rotational symmetry, just like there was in the King Arthur situation. But there's a different type of symmetry present here also, which is a reflection symmetry. So for instance, going from here to here was a reflection, right? It was a reflection across this line of symmetry passing through the midpoints here. Okay, and we see that not every, while some reflection may be a rotation, not every reflection is going to be a rotation here, right? So there will be reflections that give you a configuration that rotation does not. So answering a question here is going to require us to understand more than just rotational symmetry, but this is a good start. Okay, so the next type of special subgroup I want to talk about is the dihedral group, which directly addresses our question here of dealing with symmetries other than just rotational symmetry. So how to incorporate reflection symmetry. So the dihedral group, D sub n, is the group of symmetries of a regular n-gon. Okay, so this includes both rotations and reflections. Okay, so let's go back to our picture here. Draw it on the same page rather than just keep swapping between these sheets. So here's my regular four-gon. We saw that the rotations were this cyclic group, and here's what they were. Right, here was the 0-degree rotation, 90-degree rotation, 180-degree rotation, and 270-degree rotation. So this was all of them. So then, what is this dihedral group, D sub 4? What is that? Well, this is in the most, like, you know, when I say equals here, I'm using, this is like the flimsiest hand-waving notation that I'm using. This is the group of symmetries of regular n-gon, so it's a group of symmetries of regular four-gon here. So it's going to be all of the rotations plus all of the reflections. Okay, this is not in any way mathematically precise, really. It's just me saying that it's all of this stuff, it's all of the rotations, together with the reflections. Well, what is that exactly? I'm going to write it out. So here are the rotations. I'm just going to copy them again from here. Since this is relatively small, we can just try to exhaust all of the reflections that we see, right? So what are the reflections? There is the reflection across this line of symmetry, which is going to take 1 to 2 and 2 to 1, and 4 to 3 and 3 to 4. So what reflection is that? That is 1, 2, 3, 4, written like this in cycle notation. So 1 goes to 2, 2 goes to 1, 4 goes to 3, 3 goes to 4. Okay. Notice that that reflection was not a rotation already present. So this is not a rotation. You can't obtain this permutation of the vertices as a rotation. It is a reflection. So this is definitely different. Okay, it's not one of the previously listed things. All right, what else? Well, of course, you immediately say, hey, how about reflection across that line? Okay, so reflection across that line takes 1 to 4 and 4 to 1, and 2 to 3 and 3 to 2. So this would be 1, 4, 2, 3. But are we done? Well, no. This is a regular n-gon, or a regular four-gon in this case, a square. So it's got a lot of symmetry, right? In fact, we have more lines of symmetry. I know that the way that I've drawn it is not absolutely perfect, so maybe you complain that there's no symmetry in the way that I've drawn it because I did a bad job, but just bear with me and pretend that I did a better job drawing that square. If I were to reflect these vertices across this line of symmetry, a line of symmetry, right, is a line of reflection with respect to which the figure in question has symmetry. So here, on this line of reflection, because the vertices 2 and 4 lie on the line of reflection, those are fixed. 2 is fixed and 4 is fixed. So 2 goes to 2 and 4 goes to 4. And the only thing that changes is 1 goes to 3 and 3 goes to 1. So this is the permutation that takes 1 to 3, 3 to 1, and fixes 2 and 4. And now you see the last one. The last symmetry we have here is reflection across this line. Since the vertices 1 and 3 lie on this line, they are fixed by this reflection. So 2 goes to 4, 4 goes to 2, 1 and 3 are fixed. That is the other reflection, and it's the last thing that we have here. Okay, note that the size of d sub 4 is 8. 4 of these were rotations, and 4 of these were reflections. So this is actually like twice the number of just rotations. All right, I wonder if that pattern is going to hold. So let's think about this in general here, okay? So in general, two cases. Case 1, n is even. If n is even, then there are n over 2 reflections through axes of symmetry. And n over 2 reflections through axes that pass through midpoints of opposite edges. So reflections through lines passing through midpoints of opposite edges. So the square case is like 100% instructive here. We have 2 reflections through axes of symmetry, which are these lines that actually pass through opposite vertices in this figure. And then we have 2 reflections through lines passing through the midpoints of opposite sides. So I get 2 of these types of reflections, 2 of these types of reflections, plus n of the rotations, right? So I get n over 2 plus n over 2 plus n. So these are the reflections. And these are the rotations. So this is in total 2n. But we assumed that n was even. Okay. So what if n is odd? So 2, n is odd. Rather than write out the count in this way, what I'm going to do is the following. I'm going to show you a picture of a regular five-gon that is a regular pentagon here, vertices labeled clockwise in this fashion. What is D sub 5? The dihedral group on 5 vertices. So this is all of the rotations and all of the reflections. The claim is that there are 5 rotations and 5 reflections. That there are 5 rotations is easy to see. This is just that cyclic group, that cyclic subgroup that has 5 elements to it, right, including the identity. So 1, 2, 3, 4, 5. These first 5 are exactly these rotations. Okay. The reflections then are the 5 things that follow here. What do these reflections look like? What are the lines? The lines in question are drawn from opposite vertices to an edge, perpendicular, passing through the midpoint of that edge. So there's 1. There's 2. There's 3, 4, and 5 in this way. Let's check that these reflections actually do this. So this first one that I showed should fix 1 because the line of reflection passes through 1. It's the only vertex that it passes through. So it fixes 1. It sends 2 to 5 and 5 to 2, 3 to 4 and 4 to 3. That is this in cycle notation. 2 to 5, 5 to 2, 3 to 4, 4 to 3. Okay, one more just to show you. Now this line of reflection passing through 2 fixes 2, sends 1 to 3 and 3 to 1, 4 to 5 and 5 to 4. There it is. So similarly, there are 5 rotations, and even in this instance, doesn't matter. So even in this case, the size of the dihedral group is 2n. Thus, the size of the dihedral group on n vertices is 2n always. Half of them are rotations and the other half are reflections. Okay. Okay. One more special type subgroup before I move on to actually trying to use all of this stuff to answer some of these questions. So the alternating group. What is this? So first, note that every permutation can be written as a product. Remember, this will be the last time I remind you, when I say a product here in permutation group land, this is a composition of what we could call transpositions. What are transpositions? These are cycles of length 2. So, to show this, let's take a cycle of length 3. This, of course, is the permutation that sends 1 to 2, 2 to 3, and 3 to 1. How can this be written as a product of transpositions? Well, there. Right? This will do it. How? Let's check that this actually works. Remember, we read right to left here. So what is going on here? Here, we're starting with 1. So I'm forget that we wrote this. And I'm going to try to see what this product is by doing it in my normal way with cycle notation. So what happens to 1 here? The right permutation here fixes 1. So 1 goes to 1 in this notation. Here, so 1 goes to 1, but 1 goes to 2 on the left. So 1 goes to 2. What happens to 2? 2 goes to 3, and then 3 is fixed by this left permutation. So 3 goes to 3. So 2 goes to 3, 3 goes to 3, so 2 goes to 3. Let's just check that this closes. We know it has to, but let's just check. So what happens to 3? 3 goes to 2 here, and 2 goes to 1. So 3 goes to 1. So yes, that permutation can be written as a product of transpositions. This is true for any permutation. So here's another example. I can also write 1, 2, 3 as the product 2, 3 times 1, 3. I could also write this cycle as the product 1, 2 times 2, 3 times 1, 3 times 1, 3. And you should check that both of these, in fact, match. So there's not a unique way to do this. We can also write, say, give you one more thing to check if you want to practice. So we take a product of 2 cycles like this, 1, 2, 3, 4, 5, 6, 7. This can be rewritten as a product of transpositions. 1, 2 times 2, 3 times 3, 4 times 5, 6 times 6, 7. Okay. Now, again, this isn't the only way to write this either. I could do this in other ways. There are other transpositions I could write down here and have a different product of transpositions. So there's not a unique way to do this. So you might find it kind of annoying that there's not a unique way to do this, that there's so many different ways to do this. But while there's not a unique way to write a permutation as a product of transpositions, one thing is invariant amongst these things, which is that even though it's not unique, it's always either always even number of transpositions, or always odd number of transpositions. So what I mean is that while it's not unique to decompose 1, 2, 3 as a product of this permutation as a product of transpositions, whether or not it splits into an even number of such transposition is determined. So for instance, here I can write it as a product of these two, or these four transpositions. But in all cases, it is even. So 1, 2, 3 is even as a permutation, while this permutation is odd because I can write it as an odd number of transpositions multiplied together. And any way that I write this as a product of transpositions is going to necessarily be odd here. That's always how this is going to work. Okay. So maybe I'll write that out. If a permutation pi always decomposes into an even number of transpositions, we say it is even. Otherwise, it is odd. Okay, notice the identity permutation is even. Y can be represented as a product of zero transpositions. This allows us to define this last named special group that I wanted to talk about, which is the alternating group. The alternating group A sub n consists of the even permutations of S sub n. All even permutations of S sub n. Okay. Let's just do a quick example here. A sub 3 is simply the identity, the cycle 1, 2, 3, and the cycle 1, 3, 2. Those are the even ones. Okay, this is actually also equal to just the cyclic group on 3 vertices or 3 letters. A sub 4 is bigger. It's a little bigger. So it is. This consists of the identity. Consists of 1, 2, 3, 1, 3, 2, 1, 2, 4, 1, 4, 2, 1, 3, 4, 1, 4, 3, 2, 3, 4, 2, 4, 3, 1, 2, 3, 4, 1, 3, 2, 4, and 1, 4, 2, 3. in this way. It turns out that this size is n factorial over 2. Intuitively, of course, you might have already guessed this just because the size of S sub n is n factorial. All right, the number of permutations on n objects is n factorial. This is all of the even permutations, but I just told you that it splits as even and odd permutations, so thinking intuitively that this is half of those is not crazy, right? Okay. So here's the size of our alternating group. Here is a fact. This might seem to have nothing to do with anything, but actually, it is related to some pretty, some things that you wouldn't think it's related to, involving computing the roots of some polynomials. This is non-abelian. For n greater than or equal to 5. Okay. All right. And so, this brings us to the big question. How are we going to use these? To solve those original problems? So, let's go back to these original problems. So we had, how many ways can King Arthur and his knights sit at the round table? The symmetry that's present here, right? So we specifically phrased these problems in a way to illustrate what it meant to count an arrangement when there's symmetry present, okay? The symmetry present in this first example is rotational symmetry. So that involves the cyclic group, which we can think of as the rotational symmetries of an n-gon, a regular n-gon. This second question has us considering rotational symmetries together with reflection symmetry, so the symmetry group in question is the dihedral group, right? So that's well and good. That allows us to at least kind of categorize or organize our thoughts a little bit, but how does this actually help us come up with a number that counts these sorts of things for some examples? Well, to see this, let's do the following. So I want to come up with kind of a general method for counting combinations when we have symmetry. Okay, so we have a set of objects S. We have C, which is a set of colorings of these objects. And then we have G, which is a group of permutations representing symmetries possessed by configurations of the objects. So group of permutations representing symmetries possessed by configurations of the objects. Okay. Now, what makes two colorings distinct? When I write out my set of colorings, how do I know that I've got them all? How do I know that I've stopped listing the colorings? So, big important fact, we consider two colorings in C to be equivalent if one of the permutations in G transforms one coloring to the other. So, for instance, going back to our original problems, equivalent colorings would be ones that are taken into each other by one of these symmetries. Okay? So, for instance, the coloring, if we start here and go clockwise, and we say this is red, blue, red, green, in this way, this coloring, blue, red, green, red, these two are the same. These two are equal to each other because one is taken to the other by this reflection. Okay. Similarly, this would be the same as the coloring here, GR, BR. So both of these are equal to GR, BR here because this, I can go from this coloring to this one by a rotation. Okay, a rotation by 90 degrees clockwise. So this is exactly what it is that's going on here, and thus the thing that I'm trying to do is like the goal. All right, what is the goal here? I want to determine the number of non-equivalent colorings in C. Determine the number of non-equivalent colorings in C. So this really gives me the number of different colorings of the objects in this sense. Right? Again, notice even in the two examples I gave, the context made it clear what symmetries we were interested in. So, for instance, in the case of King Arthur and his knights sitting around the round table, we were just interested in rotational symmetry. In the case of these necklaces, we were interested in rotational and reflection symmetry because we think of this as being able to turn the necklaces over. Right? We turn the necklaces over and the beads are indistinguishable, and if they're, these kind of like spherical ellipsoid beads or whatever, I can't tell whether I'm looking at the top or bottom of the bead. Right? The example makes less sense in the case of Arthur and his knights because if we had reflected them in a way that they were like turned over, we'd be able to tell it, right? With humans, you can definitely tell typically when you turn them over. So that's the difference in the context here. Okay, how do we do all of this? Maybe it helps to do like a full example again, and just because it's small enough in order to do this, let's go back to our favorite regular foregon, this square that we've been drawing. I'm going to label it in exactly the same way. But, so this is the configuration in question. So, for instance, the object in question are, you could say a beaded necklace like this, right? So S is the set of vertices. Here's the example that we're going to do. S is going to be the set of vertices of this regular foregon, this square. Okay, so this is the set of vertices. Okay, C is going to be the set of all possible colorings of these vertices using two colors, red and green. So a set of all possible colorings of these vertices using two colors, red and green. So that's what C is. So for instance, a quick example, like red, red, green, red would denote the coloring where vertices 1, 2, and 4 are red, and vertex 3 is green. That's what that symbol means. Then we can actually just completely enumerate the possibilities here for C, just being very careful that we've got everything. We have the coloring where all of them are green. Now we can decide which ones to make red one at a time, and then we can see other combos here. So then maybe all of them are green, but the last one's red. Then maybe all of them are green, but the third. And then maybe the first two are green, and the last two are red. And then all of them are green except the second. And then maybe we alternate green, red, green, red. Maybe we do green, red, red, green. And then maybe green, red, red, red. And then red, green, green, green. Red, green, green, red. Red, green, red, green. Red, green, red, red. Red, red, green, green. Red, red, green, red. Red, 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 green. And then lastly, all red. And I think if we were careful there, we got all of them. Okay, that's all the colorings possible. Of course, I could have asked you earlier in our discussion of combinatorics, I could have asked you to count the number of colorings in this way. You know how to do that, where where you're using two colors here and you have 4 slots to color. What the options are here. You know how many of them there are, right? This could have been done day 1 of our counting. Okay, but here they actually all are, right? So instead of just a number, we have all of them here. So now we consider two colorings in C to be equivalent okay, if one can be transformed to the other by a rotation of the square. So we're not doing rotational and reflection symmetry here. This is just a question of rotational symmetry. Okay, we'll see examples later of how to use the dihedral group instead. But right now we're just talking about rotational symmetry. So, for example, if I rotate the coloring red, red, green, red, I get equivalent colorings, which are, I mean, let's just do this one at a time, right? Let's rotate this in the way that we are going to send red to the first slot, green to the last slot, red to the next slot, red to the next slot. So we're pushing them all one slot forward. That's a 90-degree rotation. So this would be red, 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 green, pushing them all one spot forward. Pushing them all 2 spots forward. If you like, green goes to the front. So this would be green, red, red, red. And then lastly, pushing everything 3 slots forward, I would get red, green, red, red. So the coloring red, red, green, red by rotation is equivalent to these other 3 colorings. And they're all equivalent to each other. In fact, we notice that this equivalence notion satisfies some properties. And I'm going to talk about that in a second. But before I do, I'm going to define something else. Okay. So in this way, going back to the way that I was trying to come up with a general thing, G is the group of permutations representing the symmetries possessed by configurations of the objects. In this example, in this problem, I've chosen this to be rotations of the square. And so our group G here is the cyclic group on 4 vertices. Okay. Now, a permutation in G is a function on function having special properties defined on this set of objects that I've labeled 1, 2, 3, 4. That's our S here, our vertices. But the reason why I'm mentioning this is that talking about colorings, though, which is really kind of the set that I'm interested in terms of what I'm trying to enumerate, how do I translate what's going on here via the group to the colorings? Well, even though it's a function defined on this set 1, 2, 3, 4, it induces a map called pi star. Okay, defined on the set of colorings. In a natural way. Natural and normal are probably 2 very overused words in math. Maybe regular is another overused word, but it's a nice word, so it's hard to get away from it here. Natural actually has a much deeper meaning here that I'm not going to get into. That has to do with diagrams commuting, but we're not going to talk about that. So what should I say here in the natural way? Let's do a quick example. Do I have room to do it here? Maybe. Let's say that pi is the 180-degree rotation (1, 3, 2, 4). Okay, so 1 goes to 3, 2 goes to 4. So you saw how in our picture that is a 180-degree rotation. Okay, 1 goes to 3, 3 goes to 1, 2 goes to 4, 4 goes to 2. It's a 180-degree rotation. What is the map on the colorings? So I said defined on the set of colorings. What is the map that I get from this? So what is like pi star applied to the coloring red, red, green, red? The idea is that whatever this pi is doing, this pi star is rotating the coloring in the same way, right? So the coloring gets rotated in the same way. So what happens is 180 degree rotation is like two slots, right? So it goes two places forward. Everything goes two places forward and cycles back. So this would be green is going to go to the front here, right? So this would be green, red, red, red in that way. What would pi star of green, red be? Well, this G would go to this G would go to the first G, this red would go to that red, and this red would go to the first red. So this is actually totally fixed. That coloring is just sent to itself by this pi star. Obviously, right, different permutations induce different maps. That makes sense. These are different functions, so of course this induced function is going to be different for those things. Okay. And so that is key. Now, let's do a quick, you want to call this a definition or even like just a statement of some facts about these things. So, if a coloring C1 and C2 are equivalent colorings in C, then we know that what that means is that this pi star takes C1 to C2 for some permutation pi in our symmetry group. We write that C1 is equivalent to C2. Now here is where the definition, maybe I'll get rid of the definition here and move it down here. So for equivalent colorings, this is true exactly when one of these induced maps takes one to the other. This is just a very precise way of saying that one of these symmetries takes a coloring into the other coloring, right? So going back, we previously mentioned that for the coloring red, red, green, red, all of these were equivalent colorings because each of them was corresponded to some rotation of this, right? So we picked a very specific rotation, the 180 degree rotation, and saw that, yeah, it's equivalent to green, red, red, red. If I had picked a different rotation, I would have gotten one of these other colorings that it's equivalent to. If I had picked the identity rotation, it would be equivalent to itself. Okay? So this is not basically, not only is red, red, green, red equivalent to green, red, 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 it's equivalent to these other two as well, red, 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 green, and red, green, red, red. But I would need to pick a different permutation to see that, right? I would need to pick a different rotation to rotate into. So I would pick the 90 degree rotation to get this one, 180 degree rotation to get this one, and the 270 degree rotation to get that one. If I wanted to get itself, I would pick the 0 degree rotation, which is the identity permutation, right? Okay, here's our definition. This is the definition of what we call an equivalence relation. So let S be a set. Okay, an equivalence relation. You know, I don't think it's that useful to give you the full definition of equivalence relation because it involves me having to define the relation as a function on the set in a way that would actually, I think, make it more confusing. So what I'll do is I'll list some facts about this very specific, what we're going to see, equivalence relation that we've defined here. So some facts. 1, this is reflexive. What does reflexive mean? It means every coloring is equivalent to itself. How? Pick the identity permutation. Two, this is symmetric. So if C1 is equivalent to C2, then C2 is equivalent to C1. So there's no direction to the equivalence here. Okay, two colorings that are equivalent unambiguously. I don't say that coloring 1 is equivalent to coloring 2, but coloring 2 is not equivalent to coloring 3. That doesn't make any sense for us if we're using the word equivalent. So this is symmetric. And 3, it is transitive. So if C1 is equivalent to C2 and C2 is equivalent to C3, this implies that C1 is equivalent to C3. Notice that this is a fancy way of saying that this behaves like equality. That is the equal sign. Because you might notice that we have all these properties for real numbers where we've used the equivalence, or we've used equals instead, right? You might also identify some other relations that numbers can have that these might satisfy, like less than or equal to, greater than or equal to. Okay, and whether or not which of those things satisfy. That's interesting. Okay, so anyway, the point is that such an object is called an equivalence relation. Technically, you might object that yes, we've defined this for a single example, but this is a very good example of what is called an equivalence relation. An equivalence relation is a notion of equivalence of things, in this case colorings, that satisfy these properties. It's reflexive, symmetric, and transitive, and for us really that just means it behaves like the equal sign. Okay? It's not the equal sign. That's a very important fact. That's kind of the whole point here. But it behaves like it in these ways. Now, the most important thing about equivalence relations is the following. So we'll call this a 3-star fact because this is basically the main reason to use equivalence relations, is that equivalence relations partition the set that they are equivalence relations on into equivalence classes. So equivalence relations on a set partition that set into disjoint subsets called equivalence classes. The equivalence classes are set up in such a way that members of the same equivalence class are exactly those members that are equivalent to each other. They're not equivalent to something outside of their equivalence class. So let's see like a further sub-example of this. C4 partitions our set of colorings C into 6 equivalence classes. So Remember, here's our set C, the set of all colorings, okay, of these 4 vertices using red and green. Okay. So then how does this get partitioned into 6 equivalence classes? There's the coloring that's all greens. No matter what I rotate that to, it's always going to be just that, right? It's never going to be anything else. Then there's the things having 3 greens. So green, 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 red, green, green, red, green, green, red, green, green, and red, green, green, green. All of those are in the same equivalence class. Then there's 2 green, 2 red. Green, red, red, green. Red, green, green, red. Red, red, green, green. Green, red, green, red. And red, green, red, green. These are all equivalent to each other. They're not equivalent to anything outside this class. Then there's 3 red, 1 green. So green, red, red, red. Red, green, red, red. Red, red, green, red. And red, 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 green. Oh, what am I doing here? Hold on. These 2 are separated. This is a separate class. I included these. These are not included because notice that any rotation here is just going to repeat this thing. I'm not going to go from green, red, green, red, red, green, red, green to one of these things. Okay, so that's I should have written that on a separate line, but that's fine. And then lastly, all red. So 1, 2, 3, 4, 5, 6. 6 total equivalence classes. Each thing within each class is equivalent to everything else in that class. A choice of any particular thing, choice of a single element of an equivalence class is called a representative element of that class or for that class. Now the reason for this is with respect to the equivalence relation, everything in a class is just as good as anything else. So choosing one of them, you're choosing something that is equivalent to any of these. So relative to this equivalence relation, it's a representative element for its class. You could have picked any element in that class, and this would have the same property with respect to this equivalence relation. So as far as this equivalence relation is concerned, everything in one of these classes is equivalent to everything else in the class, and they are equivalent to nothing outside of their class. Okay, that's the important bit. Okay. And so this tells us, and this is the last thing I'll write before I stop for today, and we'll finish this tomorrow. This tells us that the number of ways, so number of ways to color the vertices of a square using 2 colors, discounting rotational symmetries. Color vertices of a square, discounting rotational symmetry. is equal to 6. It's the number of those equivalence classes. Because each of these in a class are equivalent to themselves, so if you are thinking of trying to count all the colorings, all of these colorings count as 1. So you're counting each class once. So then the number of distinct colorings, the number of non-equivalent colorings, is just the number of different equivalence classes, of which there are 6 in this example. Okay. And so now, first thing I'm going to do in tomorrow's lecture is translate everything for those original 2 questions that we asked. I'm going to translate everything into this new language, and then we are going to use this to solve this counting problem. So that is the plan, and that's what we're going to do. So I will pick right up from there tomorrow. So I think that's all I want to say for today. So have a good rest of your day, and I'll see you tomorrow.